The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, thank you for attending today's webinar, Really Large Queries, Advanced Optimization Techniques. My name is Elisa Baum. I am the Director of Product Marketing for Percona. We'll begin in just a moment, but first I'd like to conduct a little bit of house cleaning. The first thing I'd like to do is ask everybody to raise their hand, if they can hear me, in the control panel of the GoToWebinar control panel on the right-hand side. So can everyone just do me a favor and raise their hands if they can hear me? Okay, great. Thank you so much for that. Okay, next, during this webinar, you will all be on mute. Should you have any questions during the discussion, please enter them in the question field in the control panel. At the end of the webinar, we will take the time to answer as many questions as possible, and those questions that aren't addressed will be addressed in Peter's follow-up blog entry on Percona's MySQL Performance blog. In addition, a recording of this webinar and the slides will be made available to everyone here within 48 hours. With that said, I'd like to turn the floor over to our presenter today, Peter Boros. Peter?
Thank you, Alicia, and welcome everybody. So we will talk about large queries today, about really large queries, and how can you optimize them, how can you approach this issue. We will go through an agenda first, and in the agenda, my first point is showing the title slide. So far things are going great. That's already done. I already showed it. And next is going through this agenda. This is happening right now. Then we will talk about the prerequisites for this webinar. And for the rest of the time, we will check some case studies. The first two case studies will be a little bit easier. They are kind of a warm-up. The third case study will show a more complicated example, and the fourth one will be a real monster. All of the case studies are made up. They are based on actual cases, but in a case study I used many cases, so they are artificially constructed bad queries. Okay, I can show you more examples. So what is this talk not about? It's not about SQL basics, it's not about reading explain, and it's not about indexing basics. I expect you to know all that. This talk wants to fill the gap between the ability of reading explain for a single query, because you can read at many places that, okay, if your explain shows using file sort, that's pretty bad because MySQL has to sort your records before presenting it to you. But how does it affect a real world query, and how put this knowledge together? You think there is a gap between that, and this talk intends to fill that gap. So let's move to case study number 1. So case study number 1 is this query in the right-hand side, and the query runs in the 10 seconds range, and according to explain output it is using some indexes, and mostly single column indexes were defined on the tables which are used in this query. Let's see what this query is. If you take a glance look at the query, you can see that we have a filtering condition t.title like %d% and lower t.username like %e%. These are very typical anti-patterns in a query like this, and you may shout, oh, I could spot it, that's the issue. None of them will be the issue. This talk is about how to find the issue in such queries. So let's take a glance look first at the query itself. It is joining the table T. It things T with thing stuff and yet another table. I chose very good names, I believe. So practically, we are doing equijoins on this. At least from the query, it seems like they will be equijoined. So thing stuff and yet another table are just containing lookup data. Most likely, they are just containing metadata for the things we want to check. And all of the filtering happens on the things table. Okay, rows examined for this query is in the 100K range, so it's 100,000 rows examined, but the rows returned is only a single digit. This means that something in this query is very selective, but most likely it's not indexed, or that index is not used by the query, because we have to examine roughly 10,000 times more records than it's necessary. So let's see the explain output, okay, for the query. This is an explain output. I just ripped off the columns from the explains table, which we don't need right now. And we can see that this is really an equijoin because we can see the type EQREF on each table, on thing stuff and on the yet another table. So these are equijoins. These are not issues. The join is indexed well. The issue is with the filtering conditions. The filtering conditions on table T. So what can we do about it? First, we have to find the clause which is filtering in this query. So now that we know that the things table is guilty for the bad performance of this query, we will take the query and go one by one on the filtering clauses to see what is the selective one. Is t.active the selective one? Is t.type equals guest the selective one? Is t.title like D is the selective clause? Is lower t.username like E is the selective clause? Is t.grant and 1 is not equal to 0 is the selective clause? Or is t.attribute 1 equals 3 is the selective one? How can we do that? We can simply calculate the cardinality for each column by, we can simply calculate how many records are returned for each clause. So we are selecting the count where, and the filtering condition is t.active, and we are returning 100,000 records, so it's in that range we were talking about. So this won't be our filtering condition. Okay, where t.status is guessed, it returns 200,000 rows. Where t.title like D returns 170,000 rows, and and where lower t.username like %t% returns 190,000 rows. So far, even if these could be indexed, at least because there is roughly 300,000 records in the table. So we can see the last two are typical bad query patterns, like infix match in the string and infix match in the function of a string column or a text column or a varchar column. Even if we could index that efficiently, it wouldn't help. Why it wouldn't help? Because it matches so many records. And last but not least, the condition where t.grants and 1 is not equal to 0 is selective. So if we could use an index on this, it means that this query will be a lot faster. How much faster? Instead of examining records in the 100,000 range, we will examine only a single digit number of records, so it will be orders of magnitude faster. Okay. In the original table definition, I can tell you that the grants column has an index on it, but this is not used, and the data type of grants is tinyInt. So what is this? The AND operator is bitwise, or the ampersand operator is bitwise AND. So what happens here? It is the bitwise AND operator, and this way the left-hand side of the comparison is not the column itself, but some function of a column which is compared to the value on the right-hand side. So practically, what is happening here? We are using the tinyInt as a bitmap. Okay, we are using it as 8 bits, not as a 1-byte integer. And since the name is grant, let's assume that we are storing privileges on it. So a user has this grants column, and in this grants column, we are storing 8 privileges with yes or no values. We are storing bits practically. We are being really memory efficient, right? Or we are being really compact on the data. So the most significant bit of this tinyInt will represent, let's say, privilege A, and the least significant bit represents privilege H. So does some document or user or whatever this query represent has privilege H, that means, because the least significant bit is privilege H. One is this, if we write all the bits. So this is practically used as a bit mask. So if we do a bitwise AND on it, we on the user's documents whatever privileges, and on the number 1 we can get 1 if the user or document or whatever has privilege H, or we will have 0 as a result if the user or document or whatever doesn't have privilege H. So this is only checking a privilege. What is the solution here? We can't use an index by itself, but this is really, really compact. But the data is there, but it's not accessible. How can we make it accessible? By denormalizing. Okay, we can add, let's say, a privilege H column, which can be a tinyInt or enum yes no or something like that, which will also take up 1 byte, but we can create an index on that, and despite that its selectivity is low, it seems that not too many users or documents or whatever has this H privilege, and we check if the user has it. So here, despite selectivity is low, the data distribution can help us to use an index on this query. Okay, if other checks for other privileges are frequent and they could benefit from the index, a similar technique can be applied to denormalize those queries in separate columns. And for the other typical anti-patterns in the query, like t.title like and other function on the left-hand side, they just don't matter. Okay, there is no point in optimizing them, because even if we could use an index on that, we are already examining only 4 records. How can we make it better? By examining 2 records or something like that? It's not worth doing it anymore if we have this optimization in place. Okay, so in this case we solved this issue with denormalization by adding an extra column to the table, which contains data which is already in the table. It just contains it in a more accessible and in a more indexable form. But the point of this this case study was to show you how can you approach these types of issues. How can you break down a relatively larger query into smaller parts, examine the smaller parts by themselves, and identify the issue. And let's move to case study number 2, where I can show you, a similar case study. We have 3 tables in this case: table A, table B, and table C. And we have some where conditions. We are using a comma join here, the comma join syntax. So the join conditions are appearing in the where conditions also. And we have some filtering conditions on some tables. And that's it. So what should be the issue? Let's take a look at explain. On table B, the type for the data access is equal eqref. On table C, it's ref, but the table A is the index, is the issue itself, and it is using an index on attribute 3. And if we check table A.attribute3, it says non-selective, so I got some hint in this query itself that this won't be the good index to use. So we have to examine if there is any selective stuff we can use, and what would that be. And what is also interesting here is in the possible keys section of table A, index on attribute 4 is listed also. So it's a possible index, but it's not used. And if you check the query itself, and table A.attribute 4 equals an exact very large number, this seems to be really selective to me. Even by not looking at the data, this seems to be, this seems to be very identifier-like. So let's apply the same technique. You can apply the same technique to find out the filtering condition. And if you are applying the same technique and do where table A.attribute3 equals non-selective, it will return a lot of records. When table A.attribute4 equals this, and it will return, it won't return too much records. So this is very selective. Okay, and if we do a show indexes, show index from table, then we can see the 2 indexes. And indeed, for the attribute 4, the cardinality is 21. And if we check the column definitions, they are both varchars. They are both varchars. But this is not quoted in the query. So it's a varchar query, but we are using an integer to query it. Okay, this is an integer stored in varchar column. It is not a good practice, but still I see this from time to time. And if you are quoting numbers and not quoting strings, it can be an issue. So if we change the query to this, which is the same query, but this quoted, after this change, the right index is used. How can we overcome this issue? Apart from that, we can overcome this with changing the data type of attribute 4 if it's really a number. And if it's really a number, it is our best option to change the data type on attribute 4 itself. So in this case, I I didn't show you how to check which part of the query is causing the problem here. I showed you that at case study 1, but a similar technique can be applied to find what is wrong. So this example is not that different from case study number 1. And the only difference is that the issue is different. Here we have a data type mismatch. A similar thing can happen if you are joining two tables and the identifier used in the join is, for example, integer in one column and varchar is the other varchar on the other column. Then the join won't use an index, and it is much harder to detect that than in this case. And I saw even that a few times by now. Let's move to case study number 3, which will be a more complex example or a more complex query. So this is the query we will optimize. It's simple, isn't it? So if the query is big enough, and big enough I mean you don't know where is what, always start with formatting the query. Okay, so this is really important. It can really save you time to format it properly. Okay, we formatted it, so now we understand what it is doing and didn't explain on that. And the first issue in the explain output which we identify is that that part of the query is a dependent subquery. So how can we overcome that? So we are selecting from the things table. We have a lot of conditions, right? And we have a dependent subquery, which will mean that this will be a full scan on the outer table, which is unfortunately containing 24 million records. So this is the first issue we have. Let's see how can we overcome this. Of course, here the end is not necessary, just where not exists. Let's say that there is some other conditions here. So we should rewrite this to this. If we are using a not exists query, that can be rewritten to a left join, because with the left join we can look up data in one table which is not in the other table. So it's the counterpart of a not exists subquery. And with this, we will have the possibility to use an index on this. Okay. Let's see how the explain change. It looks a lot better. The query is a lot faster after this rewrite, but let's say it's still a bit slow. We are using the index idx important num other range, which is a compound index on important number and on other range value. Okay, so just to make it clear, this was the explain output of the rewritten part of the query. And we are using a composite index on important number and other range value. Yeah, an is null condition is most likely not selective. These are most likely selective. But what is the issue? These are two range conditions. So even if we have a composite index on them, both of them can't be used. Only one of them can be used. So what can we do in this case? First, we should check if it's really an issue if we can use only one of them. How can you see that we are using the index only an important number? You can see from key length 4. It contains 2 integers, but the key length used is only 4 bytes, which is 1 integer. So in this case, we are not using an index on other range value. Let's examine if we can benefit from using an index on other range value. If we select the count for the important number, where the important number is between 1 and 4, the count is this, so it's close to the estimation of the optimizer. And if we are selecting the other count, that one is higher. So if we have to choose from the two of these, really the important number is a better choice than other range value. But do we have to choose? So how filtering are they together? And together they only return 100 records. So these two conditions together are really selective. Both of them are range conditions, so they can't be used together in a composite index unless we rewrite. And with this example, I wanted to show you how can you rewrite a range condition to a non-range condition query. So if you rewrite this to a query which selects the distinct values, then key length will be 8 and this query will be fast. So let's say that that we did a good job on optimizing this. We made it a lot faster. And this technique to convert range queries to non-range queries is interesting even in joins. If you have a range condition in joins and the range condition itself is composed from distinct values, you can choose to create a junction table with all the possible pairings in it. And if you join one table to the junction and the junction to another, because you have the possible values in it, that will no longer be a range condition, and most likely you can, despite that you have another table in the join and you have some more data to maintain, most likely you can use better indexes on it. Okay, so let's put this, what we wrote in the original query. And the original query is still slow even after this optimization. A lot more rows is examined than returned. So, and if we check the query, if we check the explain output, the extra column is showing that using union IDX thing ID and IDX other thing ID. So let's check the query itself. Now we are at the filtering conditions part. The join condition is no longer the join itself is no longer the bottleneck. So let's see what we can do here. We have things ID and we have other thing ID. These seem to be really, these seem to be really filtering. So we are checking thing ID in one table and we are checking in the other table that it's not the opposite. So these must be really filtering. And indeed they are. And these are large tables with large indexes. So if we want to get, like in the first example, the problematic part of the query, so we want to construct a simplified query which shows a similar behavior as the original one. And if we optimize that, the original one will be optimized also. And that query is this, where thing ID is this, or other thing ID is this, and thing ID is not this, and other thing ID is not this. Let's say that this is a site when you are searching for things, but you don't want to search for your things. Okay? And we are using an index merge. The cost of the index merge itself will go up if the query is larger. So, if the indexes are larger. So, can we avoid index merging here? because we have an OR condition, right? And the answer for that is yes. We can use a union, and we can use two queries, one for one part of the OR and one for the other part of the OR. So union, on the other hand, always creates an undisc temporary table. Basically, most likely, if you have large indexes and you are using index merge on large indexes and your result set is small, it's better to do that with union. But if the result set is large, then the bottleneck will be union itself when it creates the undisc temporary table. In cases like this, when you have expensive index merges, turning them off completely can solve most of the issues. You can do this through the optimizer switch variable. You can turn off various optimizer plans that way. Okay, so putting it together, put the rewritten query back to the original one. So the rewritten query is like this. Okay, it continues here. So this is on the left-hand side, you can see the first part of the union. On the right-hand side, you can see the second part of the union. And this query will be fast. Again, for example, you may see that we have a lot of range queries on date, and again, and even with OR conditions, and again, it's a very typical anti-pattern to have a lot of, range conditions in certain queries, but these were not the issue. The issue was the range condition in important number and other range value, and the issue was the index merge. Okay, so this query is fast enough. If I remember correctly from the cases I put this together, from the multiple seconds range, we went down to the single-digit millisecond here. Okay, let's go and check out the real monster query I was talking about in the beginning. So the case is we have a very large 20-table join. Explain looks okay. The query runs for almost an hour, but the handler status variables are way off what we should see based on explain. And this gets me to a very important part I would like to talk about. So what's the difference between explain output and show status like handler %? Handler operations showing the actual call to the storage engine. So you can use flash status, fire the query, then show status like handler %, and you can see what storage engine calls did MySQL do. And the difference between explain and this is explain shows you what MySQL intended to do, so what MySQL wanted to do, so it's just a plan. But this shows you what MySQL actually did. And these two can be really different. Okay, let's go back to the case study. And if you are tuning and explain seems okay, you should always check the handler variables. Okay, so I didn't even try to put an unformatted version of this on the slides. So we are selecting some formatted values and a lot more columns from a main table, joining metadata tables, metadata table 1 and metadata table 2. So we are left joining the main table to metadata table 1 which is joined with metadata table 2 on some attributes and with some filtering conditions. And we have metadata table 3 and 4, so this is practically almost the same. We have metadata table 5 and 6. This part is practically almost the same as the previous, but we have a lot of metadata tables, and we have where main table that important flag equals 1. So if we check the explain output, for the main table we are examining like 1000 rows, which is not much. And for the metadata, so this plan doesn't look bad at all. But from the very high number of handler read random next calls, we can say that this is handler read next calls, that we are reading too much index values here. So this is incremented when we are reading an index value, and practically this means that we are hitting the index at random parts with 60,000 times, and we are reading the next value in the index in the b+3 a lot. So if we find an index value, handler read key is incremented, and after that we are reading subsequent or previous values in subsequent values in the index. Okay, so let's see what's the issue here. To identify the problematic part of the query, let's examine a block like this. So we are joining only to two metadata tables, and we are selecting the average. So if you want to make sure that that you are selecting a lot of data from the table, but you don't want huge output, you can do select average length of some field. It will have to examine all the values in the field which are matching a certain condition. Or you can just do select star and set the pager to MD5 sum. So we are joining to metadata table 1 and metadata table 2, where M1 where a constant in metadata table 1 is some text. Practically this is what is in the parentheses in the left join. And the explain shows a very different result for this. And MySQL actually executes the join like this because of the parentheses. It will join metadata table 1 to metadata table 2, and it will join the resulting table to the other one. So one of these problematic parts take roughly 3 minutes. The original one took an hour. So 20 times 3 minutes, it adds up, right? How can we rewrite it without parentheses? If you are using left join to a table like this, that means you want to search for records that doesn't exist in metadata table 1 and metadata table 2. So you can expand this to select main table, left join metadata table, left join metadata table. And this will show our original explain output. And the query runs in 0.2 seconds instead of 3 minutes. So we did a good job. So after rewriting, after applying this rewrite to the monster query showed before, it runs really fast. But and usually this is the case. Usually people say that, okay, we have this large query, but it must be expensive because it's large. Okay, it's simply not true. You have to, in order to optimize them, you have to break them into pieces and optimize the various pieces by themselves and put the optimized piece back to the original query. Okay. for similarly large queries, what often happens is that even explain itself is slow. When I had a case, when a similarly large query joined with tens of tables, executed in 4 minutes, and explain looked good, used handler operation looked good, but if I executed explain, I saw that explain takes 4 minutes. This means that MySQL spent time in the optimizer itself to construct the query plan. And if you have queries with many tables, this I think it happens more often than I thought it at the time when I first read about this. Okay, the solution for that is to use straight join or to set optimizer search depth. So if you have large queries, straight join can really help you in such cases. Even if you are optimizing the query and constructing the relevant parts, it's worth to execute the query with straight join and then execute it without straight join to see how MySQL reordered your join, and you can get ideas from there also. So all of this is not really exact science. The goal is always that if you have a large query, you have to identify which part is causing the issue and solve that part. And with that part solved, you have to examine it again, see if it still has issues, and if it has issues, identify the next part of it which can cause an issue, and solve it, and do this until you have the query optimized. My goal is to, or another moral of the story is to tell you that even if you see typical anti-patterns in such large queries, usually, or there are times when these are not an issue at all. Okay, like in the first case study we had the infixed string matches. It wasn't an issue, but it's a really famous anti-pattern. So you should always identify the issue first and focus on what the issue is. So that is what I expect you to take away from this presentation. Okay, we will have the MySQL conference in Santa Clara this April with a really good speaker lineup. And apart from that, we have some time for questions, so I give it to Alicia. Okay?
Thank you very much, Peter. Okay, if you do have any questions about Peter's presentation, please go ahead and enter them into the panel where it says questions on the right-hand side, and we'll get to as many as we can. If we don't get to your question, please don't worry. We will address it in Peter's follow-up blog entry on the MySQL Performance blog. Okay, Peter, the first question is, for the solution to number 1, would another possible solution for small bit sets, at least up to maybe 4 bits, being to query where grant in, and then he has in parentheses 1, 3, 5, and 7. He says it would allow it to be used in multi-key indexes as a single column without needed multiple permission columns.
Okay, can you paste me the question?
Sure, no problem.
So this is something I have to know.
Okay, why don't I move on to the next one, and we can make sure to address that one in your blog entry.
But in general, so For the first case study, if you need denormalization, it doesn't matter what denormalization do you apply. If you can index it, that's good.
Okay.
Okay.
Thank you. The next question is, how about tiny int to medium int joins?
You won't have any issues with that.
Okay.
So if you are joining an integer to a bar chart, this was in my second case study example, the data type is different, but the issue with the data type is different because they are very different, right? Number versus string. Indexes work like they work because they have the columns of values sorted in the B tree's leaf nodes. And strings sort differently than numbers. But a tiny int and a medium int sort the same way. But it's a really good practice to have the data types matching. So if it's a foreign key, if you can join based on that, if you can have that value in one table and you need a larger data type on that, most likely you need the larger data type in the other table as well.
Okay, the next question is, using the union to replace OR conditions on where is good for all the OR conditions or only good for mixed indexes?
Sorry, can you say it again? So, the beginning of the question?
Yes. Using the union to replace OR conditions on where is good for all the OR conditions or only good for mixed indexes?
It's good for all the OR conditions in general, but you shouldn't use it on all the OR conditions, right? So the first approach, so there are two approaches to execute that. The first is doing an index merge, like we did it with the bad query, and the second is using union. The index merge is weak when you have large indexes. When you have large indexes are hard computationally to merge for MySQL. And if the result, and union has the weakness of creating a disk-based temporary table. So most likely, if your indexes are large and the result set is small, using union will give you better performance because creating the on-disk temporary table with a small result set won't have that much of an effect compared to an index merge. However, if your result set is large, then if you are using union, that large result set will be written to an on-disk temporary table, which can be easily slower than the actual index merge. So the correct answer for this question is that you can use union like that for any query you want, but you don't want to. And the correct answer for what is better, index merge or union, is the correct answer for roughly every question related to databases, and that answer is it depends. Okay. And in this case, it depends on the size of the indexes and on the size of the result set.
Okay, thank you very much. The next question is, a lot of times I find that an index on a date time would be helpful, but it would be way too unique since you can't do a partial index on a date time. Is there a way around this?
Yes, you can denormalize your data. So, for example, if I understand this correctly, you have a date time value, and what you want to do is search only for the year part. You can either denormalize to store the year in a separate column, and index that. But if it's only a year or something like that, which you can express with date time arithmetics, then what you can do, for example, if you are looking for data in the year 2011, you can do where date type column is greater than 2011 1st of January midnight, or where date time column is between 2011 1st of January midnight and 2011 1st of January midnight plus interval 1 year. So you can use the date time arithmetics, which is built in MySQL with plus interval or minus interval or things like that, if it's not too special and you can express with it. And that way it will use an index. If you are using, for example, the date diff and time diff and functions like that, on the left-hand side, you won't use an index.
Okay, and the next question is why we should never put quotes around the values of numeric type variables in queries.
Because that will be a string literal. Okay, and strings are sorted differently than integers. So what will happen in MySQL is that a type conversion will happen normally, but in certain edge cases, the index simply won't be used because of the data type mismatch. Okay, and when this edge case comes, usually people don't remember that this is most likely the issue. So the answer is because they will be different data types, and they won't be able to use indexes because strings are sorted differently than numbers. And an index works because it has the values, the column values sorted in the leaf nodes. It has the values in sorted order.
Okay. What is your advice on multi-column indexes with regards to selectivity, selective columns at the beginning or end?
Selective columns at the beginning. Okay, that way when you hit the index, if the first column in a multi-column index is selective, is more selective, then it will be a lot faster. This is a good general advice. However, if you know that your data is special, for example, you have a column with a very low selectivity. For example, I don't know. Let's say you are storing people in the database, and I don't know. Does, for example, do the guy has a pacemaker, so he can't enter to somewhere because it's dangerous for him? If you query that, that is a yes/no value, which will have low selectivity. But since you know that the data distribution is different here, and your condition selects only a few records despite of the bad selectivity on the column itself, you can put it first into multi-column index. Okay, so the moral of the story is that MySQL doesn't take the data distribution into account. In general, in a multi-column index, you should put the more selective in the first one. But if you know your data and you know what you are doing, then you can put a least less selective column first in a multi-column index if you know that the data distribution is special enough for that, so your query will be faster.
Okay, next question. How do you correctly manage the range condition on dates for grouping on dates, like extract the average on day, week, or month?
Okay, can you say it again? How do you manage?
Yes. How do you correctly manage the range condition on dates for grouping on dates, like extract the average on day, week, or month?
Okay. So if I understand this correctly, it is grouped by some date column, and you want kind of monthly roll-ups. But if you are selecting the average, then you have to read all the data for the given month. So you can't use an index for the group by itself. However, if you are using other type of aggregations like max or min or something like that, then if you can have an index on the given month, then you can use an index for the group by. So your aggregation, which in this case selecting the maximum value, can actually use an index for this. So in this case, in the explain output, using index for group by appears. And for this to happen, you have to denormalize. You have to put the months in a separate column. There is no way around it, because the date time will contain a more precise date. And in order to group by only the months, you have to use a function. But if you use a function of the column, you can't use indexes on them, because the index contains the column value itself and not the function of the column. So in that case, you can do it only with denormalization.
Okay, we have time for one more question, and that is using in instead of ranged conditions always better, or does it depend on the indexes?
It's not always better. So it has a turnover point. First, if you have a range condition that can't be translated into an in list, then you are quite stuck with the range condition, right? So for example, if you are storing real values or float values, which can have infinite values, then a number between 1 and 2 can't be converted into an in list, because the number is a float. If it can be converted into an in list, the range condition by default will have a better performance, because in the B tree itself, it can use a traversal link, between the B tree nodes. So instead of using handler read key, it can use for each value it gets, it can use handler read key and handler read key next for the subsequent values. So range condition by itself in InnoDB normally performs better. What I showed you is a special case when you have two range conditions and you can't utilize any indexes for any filtering conditions after you have a range condition. So if you have two range conditions, maybe it's worth to convert it to equalities. So you have an opportunity to use other indexes. But by default, if you have only, for example, numbers between 1 and 10, and you have the in list 1, 2, 3, 4, 5, 6, 7, 8, 9, up to 10, then the in list will be slower if that is the only filtering condition. Okay, the technique I showed you only helps when you have two range conditions and you need to use indexes on both of them. Similarly, if you have two range conditions in a join and you need to use indexes after that, then you can do the junction table trick to convert them to equality.
Okay, thank you very much, Peter. And everybody, thank you for attending our webinar today. We will make a recording and slides available in the next 48 hours. And